Hi guys, this is Miss Montguire. As you know, I'm proctoring the WKCE testing today, so I can't be there with you. But because a lot of the biology classes do have class this week in the afternoon, I don't want us to fall too far behind, so I put together this little video in lieu of a regular lecture. So today's bell ringer is, why is water important to life? I'm going to ask the substitute to pause the video for a moment to let you write it down, and also for you guys to discuss it as a class. So substitute, if you wouldn't mind, please take a few volunteers for people to suggest, for people to suggest their questions or their answers. Okay, so hopefully you came up with some pretty good suggestions. We'll cover why water is so important to life today during class, as well as possibly tomorrow as well. So we're in chapter 6.3. We've been in chapter 6 since we started the chemistry unit. For those of you following along online on your books, that's where we are. And if you look, water has a number of very, very important characteristics that make it really important for life. The first reason is simply that it's really abundant on Earth. It's 70% of the Earth's surface, and most animals are at least 60% water. Humans, I think, are around 68, 70%. It varies from species to species. Even plants are very full of water. Think about the leaves that are falling or that have fallen already. When they're on the tree, they're nice and soft. You can bend a leaf pretty easily. On the ground, they're all crinkled up, and if you step on them, they're crunchy. That's because they've been dehydrated. The water is gone from them. So water is probably the most recognized chemistry component on the planet. It's H2O is its molecular formula, and what that means is that water is made up of 2 hydrogen atoms and 1 oxygen atom. So the formula H2O, it's, in order for me to make this video, I had to convert my PowerPoint a little bit, so it's really written like this, H2 down below, and O, and what that means is that we've got 2 hydrogen atoms and 1 oxygen atom. Now what you may notice about this is that the oxygen atom is much, 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 much bigger than the hydrogen atom. The hydrogen atom's a really small atom. It's only got 1 proton, 1 electron, and 1 neutron. The oxygen's much, much larger. And you'll notice also that it has kind of this Mickey Mouse shape. It's because the 2 hydrogens are smaller, and also this angle between them is a little over 100 degrees, and that creates kind of the teddy bear or Mickey Mouse shape. This is the drawing that you should draw in the top right-hand box in your picture, or in your notes. Except when you draw it, you should draw it without my additions to it. Let's see if I can get rid of those. It's not letting me, so imagine that they're gone. I'll draw it over here for you. Once again, an oxygen atom, very large, that's oxygen, and a hydrogen, and another hydrogen. Okay, so like I said, water is very, very important, and it's the only molecule that exists on Earth naturally as a liquid, solid, and a gas. Other things, for example, metals exist as solids and then can be melted and become liquid, but they don't ever turn to gas on Earth naturally. And conversely, hydrogen, for example, that never is in solid form on Earth, but on Earth, water exists in all 3 forms. What's interesting is that we're looking for water in other planets, other places in the solar system, and the reason why we're looking for water is because that is the key sign of life. That is what determines whether life can exist. One of the main things. There's several things. And so when we go to Mars, for example, they're taking soil samples. The rovers and whatnot that are climbing around on Mars are taking soil samples looking to see if there's water, and we're finding it all over the solar system. However, we're not finding it in liquid form in very many places, certainly not all 3. Some places we do think has liquid form, like one of Jupiter's moons. Underneath a layer of liquid ice, water ice, we think might be liquid. So when we think about where life can exist, that's our number 1 question is there water there? So water is very, very important for life's processes. So before we go on, I want to take a little bit of time and review. So let's recall that oxygen, here's our water, oxygen has a lot of protons, 16. And each of the hydrogens just has 1. So if you're an electron being shared between hydrogen and oxygen, and you're shared right here, 1 each, 1 for each hydrogen, and you're moving around the atoms, remember it's a covalent bond, that means the electron is shared around both, but in reality it's not shared evenly like that. In reality, the electron is spending much more time going around oxygen than it is going around hydrogen because of all these protons in the middle. The protons, of course, have a positive charge, and that electron is going to be much more drawn to them than it is drawn to the hydrogen. And so consequently, both of these guys are going to share their electrons in a covalent bond, but it's a polar covalent bond, meaning it's an uneven sharing. At any given time, when you look for the electron, you're more likely to find it around the oxygen, down here, than you are to find it around the hydrogen up on the top, the 2 ears of Mickey Mouse. So remember that positives and negatives, they kind of cancel each other out, making it 0 charge. But if you are missing a negative, then what you've got left over is the positive, and consequently, hydrogens, because most of the time they're missing the electron, it's hanging out down here around oxygen, they act like they have a positive charge. And so what this creates is 2 different sides of the molecule, or 2 poles. And that's why we call it a polar molecule. Alright, so let's get some notes on this. So, remember, water is a polar molecule, and that again happens because oxygen has a lot more protons to attract the electrons. And because of that, the electrons hang out around the oxygen, creating a molecule that acts like it's got Oh gosh. There we go, that's better. We're creating a molecule that acts like it's got a positive and a negative charge. It doesn't really, because the whole molecule is neutral. They are sharing that electron, and so that electron does occasionally zip around the hydrogen, but it acts like it has... trying to highlight it's not working well, sorry. It acts like it's got a positive and negative charge. Okay. This is what's called polarity, and that creates a lot of really, really important characteristics. My slide's down there a little bit. So, now the end of it got cut off, I apologize. So, the fact that it's got this polar polarity to it, or poles on it, allows the molecule to act like it's got these charges, and what happens is each side attracts other things that have charges. So the hydrogen, which has a positive pretend charge or partial charge, attracts to things that are negatives, including the negative side of other molecules, other water molecules. So a charged pole of one hydrogen bond, of one water molecule, will attract the charged pole of the other. So that's what's called a hydrogen bond. Hydrogen bonds, by the way, and my highlighting clearly isn't working, but this is a vocabulary term. You'll want to make sure you highlight. As is polar molecules, another one you'll want to make sure you highlight. A hydrogen bond is just an attraction. It's an intermolecular force, meaning it's between molecules, not within one. And it's an attraction of a molecule towards another molecule that has a charge. Each of these attractions are fairly weak. They're not real strong attractions, but like Velcro, they're very strong in number. So, I don't know if you've ever played with Velcro before, but Velcro has all these little hooks in them. It acts like these little hooks right here. Each hook is kind of not real strong. In fact, look at this. It hardly looks like it's holding on to any of these loops. That's the soft, squishy side. But when you put them together, each hook most of the hooks grab onto one of the loops, and it holds it together. Think about when you were a kid and you pulled Velcro apart. You didn't pull it all at once. You peeled it. And that's because one at a time, each little hook very easily let go of the loops. But all together, it doesn't. So let's talk more about hydrogen bonds. Unfortunately, when I converted the PowerPoint into this presentation for me to record it, the animations kind of went away. But what do you think would happen if I have the positive charges here on the hydrogen and the negative charges, pretend charges, remember it's really neutral, but the negative side of the molecule the oxygen side of the molecule acting negative? What do you think would happen if I put two molecules together? Well, hopefully you were thinking to yourself, well, geez, if I got a negative over here and a positive over here, this positive and this negative are going to be attracted to one another. And that's exactly what happens. When you put two water molecules together, eventually they stick together. If you add another, once again, you stick together. Notice the oxygen side of one molecule sticking to the negative side of the other molecule. You put even more in. And pretty soon you start to get a negative. So here we can see that there's one water molecule, this guy in the middle, and these dotted lines are representing hydrogen bonds. These little squiggly things there, they're saying that it's a partial charge, or in other words, it's acting like a charge even though it really doesn't have one. And so the hydrogen atoms have a partial positive, the oxygen atoms have a partial negative, and they attract to one another. Now be very, very careful because a lot of people get confused with the term hydrogen bond. So the term hydrogen bond, a lot of people tend to think this hydrogen is this bond, and that is a bond with the atom hydrogen, but this bond that holds it together, remember, that's a covalent bond. It's a polar covalent bond, but nonetheless, it's a bond. Whereas what we're actually talking about is this relationship right here, this attraction between the molecule. Okay, so you've got another box up in the top corner. The first one was just drawing the hydrogen molecule by itself. Now you've got another box below that that says draw a hydrogen bond. So once again, this is absolutely the hydrogen bond. Remember, it's not really a bond, it's an attraction. As the picture indicates, this is a covalent bond. It's not really sticking out there like little alien antennas. It's just trying to emphasize that this is a covalent bond. In reality, it looks more like Mickey Mouse with the hydrogen atoms stuck right together because this space is really just the moving of an electron. So, draw this with the dotted line. Again, it's not really the shape, but it makes it easier to draw. I'm going to stop talking for a couple seconds and let you draw it. Okay, so hydrogen bonding is basically the most important thing we're going to talk about today, and really in the next day or two. And so I want to take a minute and make sure that everybody's clear on what that is. So my substitute, if you would please pause the video here, and I would like each person to pair up with somebody nearby. Don't get up once again, but like we've done several times in class, pair with somebody nearby and talk about the following two questions. So the first is, what is a hydrogen bond? And the second question I'd like you to consider is, why does water make hydrogen bonds? So substitute, if you'd please pause the video here and allow students to talk. And additionally, after they're done talking, please ask them to share with the class at large. So take a moment and pause it now. So hopefully you said that hydrogen bonding is an attraction between water molecules due to the pretend charges they have given the location of the electrons. And water has that because of that oxygen-hydrogen difference. The fact that there's a whole lot more protons in oxygen than there is in hydrogen, which makes it a lot more attractive to electrons. So, hydrogen bonding is responsible for most of water's really cool properties. As we just talked about, when you put two water molecules together, the positive side of one is attracted to the negative side of the other. And this phenomenon, this idea of water wanting to stick to itself, is called cohesion. Cohesion means means together. Hopefully you remember that from STEM. So cohesion is water sticking together. Think of to adhere, it means to stick to something. So cohesion means water sticking to other water molecules. So in this case, it doesn't technically always refer to water, but it usually does. So water sticking to molecules of the same substance. So this, too, is another vocabulary word. So make sure you go ahead and highlight that in your notes. I'm trying to highlight. There we go. Kind of, sort of highlighted. And this happens because water is making hydrogen bonds with other water molecules, and that creates surface tension. Excuse me. Surface tension is what's responsible for water beating on smooth surfaces like leaves in clean car, or what allows this bug to walk across the water without falling in. It's because it's got enough tension holding those water molecules apart that this bug doesn't penetrate it. When I see you in class next, which, gosh, will be a long time, but when I see you again, I'm also going to show you a demonstration that gives you some more examples of cohesion, water sticking to other surfaces. So here we see how cohesion forms a water droplet, a water bead on like a smooth surface like a car. So each water molecule is attracted to the water molecules nearby. And because of that, that's producing a force that holds them together. And for example, this water molecule has a force of gravity that wants it to fall downwards. But because it's attracted to these other water molecules here, it's not falling downwards because that attraction is stronger than the force of gravity. And the reason why it's so strong is because there's so many other water molecules nearby that it's holding on to. Cohesion means sticking together. Adhesion is water sticking to other surfaces because this positive negative poles that it has is very attractive to other things as well. Really anything, lots and lots of things have chemicals on them that give them a little bit of a charge, like a hydroxyl group or an OH group attached to some other kind of molecule. And so water is attracted to a lot of things, and that's the kind of thing that's responsible, for example, of water sliding up the meniscus here. You probably all experienced meniscuses. In middle school, you were taught how to measure using a graduated cylinder, and you measure the bottom of it. And the reason why it creates this meniscus, or this round shape, or the outside shape of the straw, is because water is attracted to the straw. It's attracted to the sides of the glass, and that's responsible for adhesion, attraction of molecules of a different substance sticking to water. If you're keeping track of vocabulary words, adhesion would be another one you should highlight. So cohesion and adhesion work together to do what we call capillary actions. Now, if the word capillaries is familiar to you, that's because you probably heard it in the context of health. When your heart pumps, it pumps into tubes called arteries that get smaller and smaller and smaller, and the smallest tubes are called capillaries. They're what happens when you have, for example, would draw an eye, and sometimes you see little blood vessels. Well, those blood vessels are tiny capillaries. And when you have bloodshot eyes. So capillaries are basically just the term for small, tiny tubes. Well, when you have a small tube, Remember, water is attracted to other things. And so consequently, water is attracted to the sides of the tube. That's adhesion. But when, say, this water molecule is attracted to the sides of the tube and moves up the tube, well, this water molecule is also attracted to this water molecule. And so as the first water molecule moves up the tube, it pulls with it the one it's attached to, and the one it's attached to, and so forth. So what happens is the water climbs the side of the tube and brings with it the water in the middle of the tube. The skinnier the tube, the smaller the ratio of edge water versus the water from the center, the higher the water is going to climb. This becomes very, very important for plants. As water evaporates out the top of tiny tubes in plants, and by the way, the tiny tubes in plants, if you see wood grain, that's the grain you see are the little tubes inside of plants. And so as water evaporates out the top of the plant and the leaves, the water goes, and as the water is leaving, it pulls with it the other water molecules it's attracted to and allows it to climb the tube. That's one of the main ways that water gets up from the roots to the leaves in a plant. So another one of water's really cool properties is that it has a very high specific heat. Specific heat isn't exactly a vocabulary word, but you should understand how it applies to water. So if you want to consider it a vocabulary word, you probably could. So specific heat is how much energy you have to put into a molecule to raise its temperature. In other words, how well does the molecule hold on to energy, or how easy is it for it to hold on to energy or to raise it, to change its temperature. So temperature is just a measurement of how fast the molecules are vibrating, and the hotter it is, the faster they're vibrating. And so when we say water has a high specific heat, what that means is it takes a lot of energy to make the water molecules move faster. You probably experienced this if you've ever boiled water in a pan, or in a pot. When you turn the stove on and you have the pot on the stove filled with water, very, very, very quickly the pot is too hot to touch. That's because the pot has a very low specific heat. It's very easy to change its temperature. But it takes much longer for the water inside of it to boil, and that's because you have to put a lot of energy into that to get the water to move faster. Well, remember, as I said, that a lot of water's properties are because of its hydrogen bonding. Well, remember that cohesion, or water molecules sticking to each other because they have hydrogen bonding, they make the water molecules stick together, and consequently, when they're sticking together, it's a lot harder to move. In order to start vibrating, you have to move one molecule, you have to kind of move them all because they're all kind of sticking to each other. And so it requires a lot more energy to get it moving. It also requires a lot more time and energy to get it to slow down its movement. Because once again, you're kind of doing it for all of them. And so that's because of the hydrogen bonding. Water slows up. Water is slow to heat up. It's slow to cool down. And that becomes very, very important for a couple of reasons. One, as I mentioned at the beginning of class, water is very, very plentiful in organisms. We have about 68% water in our bodies, and consequently, because our water is very slow to change temperature, it's one of the ways that humans and other organisms help regulate their temperature. They stay at a very constant temperature because the water inside of them is very slow to change. We have other mechanisms too. We can increase our metabolism and burn energy that way and create heat. But it's the water's specific heat that aids that process along. Additionally, a lot of biomes can hold life because of water's specific heat. So up at the poles, up and down at the poles, it's very cold, of course, and they don't actually get enough sunlight to provide the energy needed for life. However, because there's a lot of water in the area, the water carries the energy in it. It holds on to the energy, and it makes it much, much warmer than it would otherwise be. We see this in a less dramatic fashion when we look at chromatograph when we look at a climatograph for two different cities. So Seattle and Fargo are both about the same latitude, so they're both getting about the same amount of light. But when we look at Fargo, which is in the middle of the continent, there's no water anywhere nearby. In the summertime, its highest temperature, that's not real straight, but it's in like upper 80s. And that's an average. Remember, when we average things, they're less extreme. Its lowest temperature is down here. That's around 0 degrees. At the same exact latitude, we can see Seattle, which is right next to a giant body of water, the ocean. It gets to be kind of warm. I kind of went up there. It's about 70 degrees. Went up again. Went about 70 degrees at its warmest. But at its coldest, it's only at 40 degrees. A little below 40 degrees, 30-something. And so consequently, Seattle has much less change in temperature because it's holding heat due to the specific heat of water. In other words, the high energy holding capacity of water. So that's where we left off with in my second hour class. My third hour, I'm not quite sure where you'll get to without me, but it's a good spot to take a moment and pause. So second hour, you're coming in today, and as I mentioned, I made this video for you guys to keep going without me. And so second hour, you're starting off. Third hour, you're plugging along. You may be in the middle of the lecture. This may be at the beginning of the next day. I'm not sure. But if this is the beginning of the next day, and definitely for second hour who's starting today, I'd like you to think of the bell ringer for today. And that is, how is hydrogen bonding responsible for adhesion, cohesion, and water's energy holding, or in other words, specific heat, capabilities. PA. So second hour, this is your bell ringer for today. Third hour, if you're starting class, you can consider this your bell ringer. Otherwise, just stop for a moment and talk about it. And substitutes, I'm sorry, please take a moment and pause this so students can write it down, as well as talk about it with a neighbor and volunteer the responses to the class. Okay, so hopefully you came up with the idea that because hydrogen bonding causes water to stick together as well as to stick to other things, that's how it's responsible for adhesion and cohesion. And hopefully you came up with the idea that because of that cohesion, that makes it very hard to start the not start because all molecules are moving, but to increase the rate that the molecules move, as well as to decrease the rate that the molecules move. Okay, so now we're going to move on and talk about another one of water's awesome properties that happen because of hydrogen bonding. And that is the fact that water is a great solvent. So before we go on, I put this black box up there because I wanted to talk a little bit about it before you started writing everything down. So most of you have probably, I hope, experienced the phenomenon of doing the dishes and having to scrub the dried, crusty food off of pots and pans and whatnot. So what do you do if you want to make that job a little easier? Well, you probably put it in some water, and you let the water soak. You can use soap, of course, but simply just letting water soak on food makes it a whole lot easier to clean up, and that's because water is dissolving the food. You probably experienced this putting Crystal Light in, or Kool-Aid in water and letting the Kool-Aid dissolve, or even salt or sugar in water. That's because water is really good at dissolving things. So when we say it's a great solvent, what we mean is that water is dissolving stuff. So we got some vocabulary to get out of the way. So these are all vocabulary words. Solvent, solute, solution, mixture, all the different colored ones. Those are vocabulary words. So the solvent is simply something that's doing the breaking down. So water is a solvent. It breaks down stuff. The solute is simply the thing that's being dissolved. So Kool-Aid, salt, food, whatever it is, what's being dissolved by the water. A solution is just a mixture of the two things, but it's a mixture that is uniform. In other words, it's mixed so thoroughly that you can't tell the different parts anymore. So, for example, when Kool-Aid or Crystal Light or something like that's not thoroughly mixed, you still see the little powder granules at the bottom. But when it is thoroughly mixed and it's a solution, you can't see the individual Kool-Aid powder and water molecules anymore. You just see like pink liquid. And that's because it's mixed so thoroughly that you can't tell the different parts. So we call that a homogeneous mixture. In other words, homo meaning same, that all looks the same throughout. So mixture, solution, solute, solvent, those are all vocabulary words. You can even add homogeneous as a vocabulary word as well, or in other words, the same throughout. So water's polarity is what's responsible for this. Water, the charged poles of water is what's actually pulling it apart. So I'll give you a second, make sure you got all that down, and then we'll go on and I'll explain this a little bit more. So first off, let's just review. Here we've got Kool-Aid, and we've got our solvent, that's the water, that's what's going to do the dissolving. We have our Kool-Aid, that's the solute, which is what's being dissolved, and then together, once Kool-Aid is made, you cannot tell the individual Kool-Aid particles from the water, so we call it a solution, or a uniform mixture. So here's how it works. Salt, or whatever it is, works basically the same way. And that is, remember, water molecules has the little Mickey Mouse shape, and the hydrogens, that's these guys, they're acting like they're positive. Remember, most of the time they're missing their electron because it's hanging out around the oxygen. So the hydrogens are attracted to anything that's got a negative charge. Well, sodium chloride, that's table salt, has sodium chloride. They're both ions. It's an ionic bond. Remember, that means that the sodium lost its electron to the chloride, and it's basically, it has a part, not even acting, it has a full-on positive charge, and the chloride has an extra electron than what it normally has, so it has a negative charge. So the chlorine, which has a negative charge, is attracted to the hydrogen atoms in the water molecule that have that are acting like they have a positive charge. Conversely, sodium, which lost an electron, has a positive charge, and so the negatives on the oxygen are all attracted to it, and as it's attracted to it, it pulls that compound apart. And so, remember, likes dissolve like. I guess not remember, maybe you didn't know that, but like kinds of molecules dissolve other things. So water can very easily dissolve other polar molecules or ionic molecules, because ionic compounds, because ionic compounds are made of things that have a charge. And so things with charges like water attract and break down other things with charges. And that's sugar, that's salt, it's a whole host of things. Water is basically the universal solvent because it can dissolve more things than any other molecule on the planet. However, it does not dissolve non-polar molecules. Non-polar, remember, they're hydrophobic, or in other words, they hate water because they don't have any charges, and so they actually repel water. So water doesn't really dissolve non-polar things very well. I mentioned that water is a homogeneous mixture, meaning it's the same throughout. You probably all experience a heterogeneous mixture, and hetero just means different. We'll use those prefixes a lot. Homo meaning same, hetero meaning different. So a heterogeneous mixture meaning it's not the same throughout. Another way of looking at it is you can separate it. So I got this picture off the internet. My mom, that's one of her things that, everybody's mom has a couple of things that they make and everybody goes nuts for. And for my mom, one of the things that she makes that my entire family likes is Chex Mix. And everybody has something different. So like at Christmas time, if my dad's had the Chex Mix container, usually it's devoid of the pretzels because he really likes eating all the pretzels. If I get it, I like the Chex part, these guys here, and so I like to eat those out of the way. My brother prefers the peanuts, so did my mom, and so it kind of works out nice because everybody gets what they want. But nevertheless, we can easily sort out what we like. We can pick out the parts. We don't need to use any chemical process whatsoever. We can just pick it out, and that's what a heterogeneous mixture is. We can pick out the different parts. Not only can we pick it out, but we can see that's a nut, that's a Chex, that's a pretzel. And so we can tell the different parts. That's a heterogeneous mixture. A solution, like Kool-Aid, or like, even our tap water is really a solution because we've got dissolved minerals and ions and even fluoride added to it, and so all of those things are solutions. We can't tell the components that make it up. So here, once again, is another picture of how salt breaks down. So this is salt. Salt makes a crystal. The positives, those are sodium. The negatives are chlorine or chloride. And when they're by water, the hydrogens, the positive, all surround the chloride, where the negatives are all attracted to the sodium. And then consequently it pulls it apart. Okay, so we're in the home stretch now. We've talked about how water's polarity is responsible for adhesion, cohesion, for it holding a lot of energy, and for it being able to really dissolve things very, very well. One of the other things that water's polarity is responsible for the fact that water expands as it freezes. And that's really kind of unique because most molecules, most things, when they get cold, they shrivel up. They get smaller. But water expands. That's why ice floats. And it's really important that ice does, in fact, float. So, water molecules in everything, not just water, but everything, slows down when they get colder. That's the definition of getting colder, is the water or the molecules move more slowly. So, when water's molecules slow down or get colder, the hydrogen bonds make crystal structures. They make hexagonal, or in other words, they make these beautiful crystalline structures. That's not possible when water's moving faster, vibrating much, much faster. The structures don't hold because of the vibrations. But when it slows down, it can make those structures. And so it can go from looking like this, a jumbled up mess, to having these very cool hexagonal structures and look like crystals. So at liquid temperatures, it's moving too fast, and all the hydrogen bonds has too much energy to make the crystal. But when it's moving cooler, it can make those structures, so it makes the ice crystals. And you've probably seen the ice crystals. Yesterday it snowed, and maybe when your parents picked you up, you might have noticed that there were ice crystals on your car, on their car. And if you've ever seen a snowflake, that's the same thing that's happening, is they're making those beautiful ice crystals. And because of that formation, this takes up a lot more space than this. And so that means that there's less stuff in a given amount of space, which means it's less dense. And consequently, ice floats. So water's density is about 1. We'll talk about that in a second. Ice's density is about 0.9 grams per milliliter. Ice floats, and that becomes invaluable to organisms that live in ponds that freeze over. If it didn't float, then the ice at the surface would form when it gets cold and sink to the bottom of the pond, and then ice at the surface would form and sink to the bottom of the pond, and the entire pond would be frozen. But that doesn't happen because ice floats. So it's also responsible for a phenomenon known as turnover in ponds. And this happens, I think I even mentioned it in our ecology unit, but this happens in the spring and fall, like right now, and it's responsible for the mixing of nutrients. Nutrients being things like decayed material, phosphorus, nitrogen, even something like oxygen, which is gets into the water at the surface. Remember, oxygen and carbon and other molecules diffuse from the air at the surface. Well, if there wasn't any change in density or change in temperature, I should say density, in water, then all of the nutrients would be at the top. So in the summertime, the top areas is what's exposed to the air, and so that's where all of the new, I shouldn't say all, but many of the new resources like carbon and oxygen get into the water. You'll notice also that in the summertime, the coldest part's down at the bottom of the lake and the warmest part's at the top. That's degrees Celsius, so 22 degrees is pretty warm for water. Well, in the spring and fall, like what's happening right now, the temperature is changing, and as the top parts get colder, the water becomes the same throughout, and consequently, there's turnover. The density of the water causes it all to get mixed up, because remember, the least dense stuff is always on top, that floats. And so, the colder the water is, the more dense, I shouldn't say that, but the changing density causes it to get all mixed up. And consequently, in the wintertime, when the ice covers up over, all these nutrients get mixed up, the ice covers up, and this all can stay liquid. Alright, our last phenomenon I kind of referred to on the previous bullet point, and that is that water has a very uniform density, and that is that pure water has a density of 1 gram per milliliter. Exactly 1 gram per milliliter. Anything less dense than that will float, like ice, or even oil. Anything more dense, like metal or rock, will sink. Okay, so that's it for the water notes. What you do next kind of depends on how much time there is. I suspect that the second hour for sure will have some time to kill, so we'll talk about that more in a minute. Take a few minutes, make sure you've got everything, and then maybe talk with a partner briefly. Again, don't get up. Talk with a partner about why water expands when it freezes and how that's important for life.